Unit 7, Lesson 4, Solving Exponential Equations. So up until now, we've always worked with exponents that are just numerical. So the exponent is always just a number. Okay, but today's lesson, we're going to look at situations where the exponent has a variable present. Here are 3 examples of what I mean by that. Okay, at least one of those exponents in each situation has a variable present. So in order to solve these types of expressions, you need to make sure that first the bases are identical. Okay, the bases here are both 2, both 4, both 5. So those would be good to go, and we could solve using the processes that I'm about to explain. The reason why it's so beneficial to have the same base is because if the base is the same, then to solve for x, you can essentially just ignore the base and set the 2 exponents equal to each other. What do I mean by that? So if I was going to solve this question here, because the bases are both 4s, I can completely ignore them, and all I have to solve is 2x minus 1 equals 1. And then I can solve for x. Same thing over here. Bases are both 5, so I can completely ignore the bases, and all I have to solve is 3x equals x minus 7. Okay, so let's try out some examples here. Example A, 2 to the power of x equals 2 to the power of 3. What's the value of x? Well, the bases are the same, so I can just solve x equals 3. There's nothing to simplify. My answer is just x equals 3. Let's try part B. 4 to the power of 2x minus 1 equals 4 to the power of 1. Bases are the same, so I only need to solve 2x minus 1 equals 1. So I'm going to add 1 to both sides. Then I have 2x equals 2. I'm going to divide 2 on both sides, and we're left with x equals 1. Okay, let's try this one. We can ignore the bases, so I just need to solve 3x equals x minus 7. Okay, let's go ahead and get the x's onto the same side. Then I have 2x is equal to negative 7. Then if I divide both sides by 2, I get x is equal to negative 7 over 2. Okay, and if you ever want to check your answer, just plug that value of x back into the original equation and see if it works out. See if the left side equals the right side. Okay, sometimes you will get expressions where the bases are not the same, and you have to do a little bit of work first. So all you have to do is turn this 4 into an exponent with a base 2, and then you can proceed as normal. Here's what I mean by that. So 4 is the same as 2 to the power of 2. Okay, now we have like bases, so all I need to solve is x equals 2. There's obviously nothing to solve, so we're finished. Part B, we do not have like bases here. Okay, so let's convert 27 into an exponent with a base of 3. So 27 is the same as 3 to the power of 3, right? If you plug 3 to the power of 3 in your calculator, you're going to get 27. So we can replace 27 with 3 to the power of 3, and we don't change the question at all. But this is good now because now we have exponents with the same base. So we can do what we did above, okay? To solve for x, we can ignore the bases, and we just have to solve 2x equals 3. Divide both sides by 2, we get x is equal to 3 over 2. Okay, 4 to the power of x equals 8. We don't have like bases, so we can't convert 8 into an exponent with base 4. So instead, let's convert both sides of the equation into exponents with a base of 2. Okay, so 4 is the same as 2 to the power of 2, so I'm going to replace the 4 with 2 to the power of 2. Forget that x is still there. And then 8 is the same as 2 to the power of 3. Okay, now I'm going to simplify a little bit, so I'm going to use the power of a power rule here. And now that I have like bases, I can ignore the bases, and all I have to solve is 2x equals 3. So x is equal to 3 over 2. Okay, let's try this one. So we don't have like bases, but I can change 25 into an exponent with a base of 5. Okay, now I can simplify this by using the power of a power rule. And now I have like bases, so I can ignore the bases, and all I have to solve is 3x minus 1 equals 2x plus 8. Okay, let's try this one. So I can't convert 125 into an exponent with a base of 25. So let's convert both into exponents with base of 5. So 25 is the same as 5 squared. So I'm going to replace the 25 with 5 squared. And 125 is the same as 5 cubed. So I'm going to replace 125 with 5 cubed. Now I'm going to use power of a power rule to simplify. And now that I have like bases, all I have to solve is 4x minus 2 equals 3x plus 12. Okay, so all those examples we just did, they either started out with like bases and then it was really easy. If they didn't start with like bases, it was really easy for us to convert them into exponents with the same base. So what we're going to get into next is what happens when you can't convert them into exponents with the same base. Okay, so this first example here, 2x equals 20. Okay, naturally we'd think, okay, let's convert 20 into a power with a base of 2, but there's no way to do that, right? You can't raise 2 to the power of a number and get 20. So when this happens, the best thing that you can do to solve for x is called approximating the value of the variable. So basically what we're doing is we are finding the approximate value of the variable. Okay, so what we do is we need to figure out 2 to the power of what is 20, okay? Well, I know 2 to the power of 3 is 8, so it's got to be higher than 3. So let's try 2 to the power of 4. Okay, see what we get. We get 16, so we're not quite at 20 yet. So let's try 2 to the power of 5. Okay, and we get 32. So from this guess, we know that it must be in between 2 to the power of 4 and 2 to the power of 5. Because 20 is in between 16 and 32. So our variable x must be between 4 and 5. Okay, so now that we know what it's in between, we can start using decimals. So let's try 2 to the power of 4.1, 2 to the power of 4.2, 2 to the power of 4.3, 2 to the power of 4.4. Well, let's test those out and see how close we can get to 20. Okay, so 2 to the power of 4.1 is 17.15, so we're not quite there yet. 2 to the power of 4.2 is 18.38, we're getting closer. 2 to the power of 4.3 is 19.7. And 2 to the power of 4.4 is 21.11. All right, so we would say that x is about 4.3, because that's the closest we got to 20. So to say that, you'd say x is about, that little squiggly on top of the equal sign means about, or approximately. All right, let's try the next one. So 3 to the power of x equals 54. It's impossible to convert 54 into a power with a base of 3. So let's just start approximating. So we know that 3 squared is 9, so it's got to be higher than 3 squared. Okay, if we try 3 cubed, we get 27, so it's still got to be higher than that. If we try 3 to the power of 4, we get 81. So I know that x must be in between 3 and 4. Okay, so let's start adding our decimals in. Okay, so let's try 3 to the power of 3.1. What do we get? We get 30.14. So I'm not even close. So I'm actually going to jump ahead and try 3 to the power of 3.5. Okay, and we get 46.77. So we're getting closer. Let's try 3 to the power of 3.6. Okay, we get 52.2. Okay, let's try one more, 3 to the power of 3.7, and we get 58.26. Okay, so that's the closest we got, so we would say therefore x is approximately 3.6. Okay, pause the video, try part C on your own, and then check your answer with me when you think you have it. Okay, so there's your answer, x is about 1.8. Okay, last one, part D. We need to solve for b in this scenario. So the first thing I'm going to do is I'm going to simplify this question, right? So 4 to the exponent of 3b equals 81. I just subtracted 5 from both sides. Okay, now because our exponent is 3b, and usually we're used to working with just x's, I'm going to go ahead and let x equal 3b. Because then our equation turns into 4 to the power of x equals 81. And we can proceed as normal to solve this, okay? And then we can go back and adjust later. So let's proceed as we did in part A, B, and C. So the next thing we'd want to do is we'd say, okay, 4 to the power of 1 I know is 4. 4 squared is 16. We're not even close to 81. So I'm going to start at 4 cubed. Okay, so 4 cubed gets us to 64. We're not there yet. Let's try 4 to the power of 4. We get 256. So our answer is going to be somewhere between 3 and 4 as an exponent, and probably closer to the 3 side because 4 to the power of 4 is quite a bit higher than 81. I'm going to go ahead and I'm going to test out some decimals. So let's try 4 to the power of 3.1. We get 73.52, we're close. Let's try 4.32. We get 84.45. Okay, so that's actually closer than 3.1. So we can say right now that x is approximately 3.2. Okay, and usually we'd end the question there, but because we let x equal 3b, we now have to use this value of x to find our value of b. Plug this back into our original let statement. So if we said let x equal 3b, and now we know that x is 3.2, we can easily solve for b. Okay, so I'm just going to divide both sides by 3, and if we round to the nearest tenth, we're going to get 1.1 as our value of b.